Okay, so brothers and sisters, welcome back to the physics classroom. It's been a long time. Sorry. Good. So this episode of the BJ's physics classroom is going to take us through, continuation of heat that we have begun with. This time around, we are looking at thermal expansion and contraction in matter. So, matter is made up of solids, liquids, and gas. So we are going to look at thermal expansion and contraction in solids for today. Next time when we meet, we'll look at thermal expansion and contraction in liquids and then in gas. So let me remind you, if you have not subscribed to my YouTube channel, then please do that for me. BJ's Physics Classroom. Sorry, BJ Online. That is the YouTube channel. The BJ Physics Classroom is the Facebook page. BJ Online. Go to BJ Online, subscribe to my channel, and then turn on the notification button. That red ring at the corner. It's black, right? Yes. The black bell at the corner. Just turn it on so that anytime I post a video, you'll be able to receive a notification and then you watch it. Thank you very much. Let's continue. So today we are looking at thermal expansion and contraction in solids. So solids expand generally when they are heated and contract when they are cooled. Alright? So because of that, if we sketch a graph of volume versus temperature for solids, we get something like this. What this means is that volume expands linearly with temperature, all right, for solids. This is a general expression. Some solids may differ small, all right. Some solids may differ small. Good. Not all solids have this property. But this is a general property graph for solids, mostly metals. Good. So you can be asked to describe a simple experiment to show that metals expand when they are heated and contract when they are cooled. To do this, you need a metal ring and a ball, a metal ball. So at the same temperature, the metal ball should be able to slip through the ring, just slip through the ring. So you shouldn't have a lot of gap around it like this one. Then we let the metal ball pass through the ring to see that yes, it can pass through at the same temperature. We put the ring down, then we heat the metal ball up to some amount of temperature. Then we bring the two of them together again. This time, the metal ball is unable to slip through the ring. What that means is that after heating the metal ball, it has expanded. Good. It has expanded. So metals expand when they are heated, or solids expand when they are heated and contract when they are cooled. So to do the other side, that is contract when they are cooled, what we do is that we cool the metal that we have heated. And then we bring it again. Then we see that now the metal is able to slip through the ring. What this tells us is that the metal has contracted upon cooling. Exactly. Thank you very much. So every solid has a property with it that makes it expand or contract when there is change in temperature. Every metal, every solid has that property. And apart from the external factors, this is an internal factor with respect to the body. We call that property linear expansivity of solid. So linear expansivity. So we begin with linear expansivity. Okay. So the symbol for linear expansivity is alpha, and the unit is per Kelvin or per degree Celsius. Change in temperature is the same, whether per Kelvin or per degree Celsius. Good. So let's consider a metal of length L and temperature θ1. This metal is heated up to temperature θ2, such that there is the new length, LF, the old length, let's call it L. There's a new length LF and the change in length delta L. The linear expansivity of a metal, of a solid, is defined as the change in length per unit original length per change in temperature. So alpha is equal to change in length per unit original length per change in temperature. I hope you can see what I've written on the board. Good. Alpha is change in length per unit original length per change in temperature. Let's call this equation 1. The change in length delta L is given by LF minus L0. You know, when we subtract the old length from the new length, that will give us the change in length, exactly. So when we put this equation into this and then we solve for the LF, we will get alpha is equal to LF minus L0 all over L0 delta theta. So we make LF the subject. LF is equal to L0, you know, I carry this one will multiply this, then I'll carry this one across the equal sign. So that is going to give me LF plus, LF is equal to L0 plus L0 alpha delta theta. When you multiply this one by this, that will give you this. Then when you carry this one across the equal sign, to give you positive. We make LF the subject, then we get L0 into bracket 1 plus alpha delta theta. Take note of this equation, these two equations, equation 1 and equation 2 very well. When you are asked to find the final length, you use this formula, given all these parameters. When you are asked to find the initial length, the change in length or the linear expansivity, use this formula. Remember that equation 1 is the definition for linear expansivity. Linear expansivity is also called coefficient of linear expansion. Don't mix the two. Either you say linear expansivity or coefficient of linear expansion. You can't interchange them. They will mark you down. Thank you. Good. So that is it for linear expansivity. Change in length per original length per change in temperature. Good. Then we look at another property that we call area expansivity. Area expansivity. Now, area expansivity is also called coefficient of superficial expansion. Coefficient of superficial expansion. That one too is given by beta. The symbol is beta, the same unit. And beta is equal to change in area per original area per change in temperature. Change in area per original area per change in temperature. Or you can define it this way: the fraction by which the original area of the substance has increased or has changed per degree rise in temperature or degree change in temperature. That is what we mean by coefficient of area expansion or area expansivity or coefficient of superficial expansion. Okay, so this one to the same way, you know, if we write the change in area as the final area minus the initial area like this, delta A is equal to AF minus A0, where AF is the final area, A0 is the initial area. And we put it back into this equation and we solve for AF. We will get AF is equal to A0 into bracket 1 plus beta delta theta. A0 into bracket 1 plus beta delta theta. This is equation 3, and let's call this equation 4. Let's call this equation 4. Now what happens is that the relationship between beta and alpha, linear expansivity, and area expansivity is that beta is equal to 2 times alpha. This relation is very important. And you can be asked by WAEC to prove this relation. When you're asked to do this, this is how you go through it. When you're asked to prove this relation, this is how you go through it. So we are looking at the proof of beta is equal to 2 alpha. Alright? The proof of beta is equal to 2 alpha. Okay. So what we do is that let us have an initial substance like this. So initially at temperature θ1, the length L0 is this, the breadth B0 is this. Upon heating this metal to a temperature θ2, the length and the breadth are like this. So this is the new length, LF, and this is the new breadth, BF. You understand? So let us consider this figure and use it to prove our case. Okay. So this final change in the material is happening at temperature θ2 exactly. Temperature θ2. So from the principle of linear expansivity, from this relation, linear expansivity, we say LF is equal to L0 into bracket 1 plus alpha delta theta. Let me call this equation I. So when I do the same thing for the breadth, you know, length and breadth, alright? When I do the same thing for the breadth, that will give me BF is equal to B0 into bracket 1 plus the same alpha delta theta. Let me call this equation 2. So let me clean this. Then I will write the rest of the equations here. Let me start from here. This time around, I'm bringing it this way, right? Good. So multiplying equation I, let's call this one II, sorry. Equation I by II. Now that is going to give me LF is equal to L0. Okay, let me multiply them. So I multiply this equation by this. So that will give me LF BF is equal to, you know, this times this. That will give me this times this. L0 B0 into bracket 1 plus alpha delta theta all squared. You know, this is mathematically correct because I'm multiplying this one by this. They are the same quantities, all squared. Then I will expand this. You know, length times breadth, area. So that will give me AF is equal to length times breadth, area. B0, A0 into bracket. Then I will expand this. That will give me 1 plus 2 alpha delta theta plus alpha squared delta theta squared. Now listen to this. Linear expansivity is a very small quantity. You know, usually 0.002, 0.00003, 0.004 is a very small quantity. So because linear expansivity is a small quantity like that, the square of the linear expansivity becomes smaller. I said more smaller, sorry. It becomes smaller. You understand that? So what that means is that since alpha is a small quantity, alpha squared becomes smaller and can be neglected. Therefore, if we neglect this whole term, the whole term becomes negligible. Then we get AF is equal to A0 into bracket 1 plus 2 alpha delta theta. Let's call this equation 5. Now let's compare equation 5 and equation 4. Alright? Let's compare equation 5 and equation 4 on the board. So when we compare equation 5 and equation 4 on the board, AF, A naught, 1 plus delta theta, we can see that beta is 2 times alpha. Remember, this is an approximated value. Beta being approximately equal to 2 times alpha. This is how we go through the proof. And you can be asked to prove it. Well, I know that when you're asked to prove it, you will not find it difficult at all. Good. Okay. So, if you haven't subscribed to my YouTube channel, please do that. bjonline.com. There's no .com, sorry. It's bjonline. And then once you subscribe, turn on the notification button so that anytime I post a video, you'll be able to get it. Thank you very much. Let's continue. So we look at another term, which we call volume. We call it cubic expansivity. Cubic expansivity. This other name is coefficient of volume expansion. Cubic expansivity or coefficient of volume expansion. That is the other name for it. Cubic expansivity on the board or coefficient of volume expansion. Good. That one is given by gamma, and it is equal to change in volume per original volume per change in temperature. So the change in volume per original volume per change in temperature. So that when I represent this one by Vf minus V naught, and I make Vf the subject, I'll get V naught into bracket 1 plus B gamma delta theta. So equation 6 and equation 7. Take note of equation 6 and 7 too very well for volume expansivity. Now the relationship between cubic expansivity and linear expansivity also is that cubic expansivity is equal to 3 times linear expansivity. And this one too, you may be asked to prove it. In fact, it has even been a WAEC question before. You will be asked to prove this. When you're asked to prove it, just like I did for this, you go to the same principle. Remember that volume is length times breadth times height. Volume is length times breadth times height. Area is length times breadth. So the only thing that is going to be added is length, breadth, and height. What that means, to do this, you need to sketch a box, like this, for it. So that you can have your length, you can have your breadth, and you can have this is your height, this is your length, your breadth, and this is your length. Alright? So let me put this one here. Let me put the breadth here. So this is the breadth, this is the height, and this is the length of the box. Now, this is at temperature T1, theta 1. So when you heat this box, the box will now expand to give you a bigger box than this. The box will now expand and become something like this. So that now you have LF, you are going to have HF, and you are going to have BF. You understand? So you relate this one with this using the same principle I have done here. Go through the same process, and then finally you arrive at this answer. So I want you to do this through a challenge. Do this and send it to the WhatsApp Facebook page, and let me see who gets it. Maybe the person that gets it will get some cash, Good. I haven't mentioned any cash. Thank you very much. Any amount. That's what I mean. I said cash. I didn't mention any amount. Okay. So that is linear expansivity, area expansivity, and then cubic expansivity. These are the three properties that are associated with solids with respect to their expansion. Remember, all of them, the the cubic expansivity and the area expansivity depend on the linear expansivity. So the linear expansivity is the main factor, the property that's associated with the matter, exactly. So now factors that affect expansion and contraction in solids. 1. Factors that affect expansion and contraction in solids. Let's look at this. 1, we have the original length. So the original length affects it. 2, we have the linear expansivity of the material. And the linear expansivity of the material, that's the property of the material. Then 3, we have the change in temperature. Change in temperature. Then we can also talk of the heat capacity of the material. Remember that a material with a higher heat capacity has very low thermal expansivity or has very low thermal expansion. You understand that? So then we talk of the heat capacity of the material, the linear expansivity of the material, the change in temperature of the material, and the original length of the material. These are the factors that affect thermal expansion and contraction in solids. Thank you very much for being part of the show. In our next episode, we will look at thermal expansion and contraction in liquids and gases. And then we can then begin to solve some questions. So please, your questions are always welcome on the Facebook page. Just post your questions on the page. I'll answer it for you. If you don't bring any question, then what that means is that whatever I'm doing and you are watching, you understand it. So I can see that a lot of people are watching what I'm doing. Thank you very much. Your comments are also very important. That will help shape the system so that we can have a very good discussion here. Thank you very much. Stay blessed. Make sure you stay safe with COVID-19. Follow all the lay down protocols. And till we meet again, it's your friend BJ. Thank you.